Hello, in this lecture we'll answer two questions. In the first question, we'll find out the size of this angle x, and in the second question, we'll find out the area of this green shape. So we'll start with the first question. In the drawing, we have a quarter circle. AOB is a quarter circle. Therefore, angle AOB is a right angle, and also angle APQ is a right angle. In addition, we know that AP equals to PQ, and our task is to find out the size of angle PQB is equals to x. We have to find out the value of x, the value of angle x. So, first of all, we will complete the quarter circle to a semicircle. We define this point as point M. We completed the quarter circle to a semicircle. Therefore, AM is the diameter of the semicircle according to our construction. So it is on. AM is the diameter of the semicircle according to our construction. So AM is a diameter, it is absolutely a straight line. So if we focus on the right side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees. According to rule 3, that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have on the right side of the straight line AM at point O? We have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will extend line segment PQ by straight line until it touches the semicircle. The question is where the extended line segment PQ will touch the semicircle. We will assume that the extended line segment PQ will touch the semicircle at this point, point L. Okay, according to our assumption, the extended line segment PQ will touch the semicircle at this point, point L. So we have here peripheral angle LPL, we have peripheral angle APL, and peripheral angle APL equals to 90 degrees according to what is given as the question. And peripheral angle APL subtend on AL. Okay, again, according to our assumption, peripheral angle APL subtend on chord AL. Okay, again. According to our assumption, the extended line segment BQ touches the circle at point L, and therefore peripheral angle APL subset on chord AL. But chord AL is definitely not the diameter of the semicircle. Why chord AL is not the diameter of the semicircle? Because it doesn't pass from point O, that is the center of the semicircle. And you know that any diameter must pass through the center of the semicircle. So it is contradiction to rule 5. Please click on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So in the drawing we have a circle. This is peripheral angle AOB that is equal to 90 degrees in size, and therefore peripheral angle AOB subtend on AB, that is the diameter of the circle. But here we have peripheral angle APL that is equal to 90 degrees in its size, and it subtend on AL, that is not the diameter of the semicircle. This is contradiction to rule 5. So really, due to the contradiction to rule 5, the extended line segment PQ cannot touch the circle at point L. So in the next step, we will assume that the extended line segment PQ will touch the circle at this point H. Again, according to our assumption, the extended line segment PQ will touch the circle at point H. So we have peripheral angle APH that is equal to 90 degrees in its size, and peripheral angle APH subtend on chord AH. Again, according to our assumption, peripheral angle APH subtend on chord AH. But the problem is that AH is the chord AH is definitely not the diameter of the semicircle, because chord AH doesn't pass from point O, that is the center of the semicircle. So we have contradiction to rule 5, because peripheral angle APH equals to 90 degrees in size, and still it doesn't subtend on the diameter of the semicircle, because AH is definitely not the diameter of the semicircle. So due to the contradiction of rule 5, the extended line segment PQ will not touch the circle at point H. And therefore, actually, we will conclude that the extended line segment PQ will touch the circle at point M and not in any other point. And again, we must conclude that the extended line segment PQ will touch the semicircle at point M. Now we don't have contradiction to rule 5. Why? Because we have peripheral angle APM that is equal to 90 degrees in size, and indeed it subtend on AM, that is the diameter of the semicircle, exactly according to rule 5. In the next step, we will join points A and Q together by straight line. When joining points A and Q, we created the right and associated triangle, triangle APQ. Triangle APQ is right angle because angle APQ is right angle, and triangle APQ is an associated triangle because side AP equals to side PQ. And we have the rule that in front of equal sides in a triangle there are equal angles. So if you relate to the right and associated triangle, triangle APQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes, according to the rule that I mentioned. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and therefore it is true also in the right and associated triangle, triangle APQ. So which angles we have in the right hand associated triangle APQ? This is the right angle. Alpha plus alpha is 2 alpha. In total, they must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So 90 degrees plus 2 alpha equals to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. Here we divide this equation by 2, and finally we get that the missing angle alpha equals to 90 degrees over 2 is 45 degrees. So actually this is the missing angle alpha that is equals to 45 degrees in its size. This is also the missing angle alpha that is equals to 45 degrees in its size. In the next step, we will prove that those two right angles can go into each other according to side angle side rule. Repeat again, we will prove that the right upper triangle, triangle AOQ can go into the right lower triangle OQM according to side angle side rule. So write it down. We have to prove that the right upper triangle AOQ can go into the right lower triangle OQM, and we prove that they can go into each other according to side angle side rule. So why those two right triangles can go into each other? First of all, side AO equals to side OM. They are both the area of the semicircle, therefore they are equal to each other. We define the radius of this semicircle as R. So AO is the radius of the semicircle that is equal to R, and OM is also the radius of the semicircle that is equal to R. So write it down. Repeat again, we found out that side AO of the right triangle AOQ equals to side OM of the right triangle OQM, above the area of the semicircle, therefore they are equal to each other. In addition, those two angles, they are both right angles, therefore they are equal to each other. So actually, this is angle AOQ in the right upper triangle AOQ, and it is equals to this angle is actually angle MOQ in the right lower triangle OQM. So repeat again, we should find out that angle AOQ in the right triangle AOQ equals to angle MOQ in the right lower triangle OQM. They are both equal to 90 degrees, and therefore they are equal to each other. And finally, side OQ is a common side that belongs to both triangles. So we can write down that OQ equals to itself is a common side that belongs to both triangles. So we should prove that those two right triangles can go into each other according to side angle side rule. So I write it down. We prove that the right upper triangle AOQ can go in. This is the sign of congruent to the right lower triangle OQM according to side angle side rule. That is to say, I should prove that those two sides and the angle that is included between those two sides in the right upper triangle AOQ corresponding equal to those two sides, and the angle that is included between those two sides in the right lower triangle, triangle OQM. And therefore those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we will derive that side AQ of the right triangle AOQ is equal to side QM of the right triangle OQM. And again, from the fact that those two right triangles can go into each other, we will derive that side AQ of the right triangle AOQ is equal to side QM of the right triangle OQM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. Okay, so we actually found out that AQ equals to QM. So if you relate to the associated triangle AQM, triangle AQM is an associated triangle because AQ equals to QM. So if you relate to the associated triangle AQM, we have the rule that in front of equal sides in the triangle, we have equal angles. So in front of those, in the associated triangle AQM, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other. Okay, so in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule actually is rule 8. According to rule 8, an exterior angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. Again, an exterior angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. So in the drawing, we have triangle ABC that could be any triangle. Those triangles alpha, beta, and gamma are defined as n interangles because they are located inside triangle ABC, while this is angle E, angle ACF equals to E according to our definition. Angle E is located outside triangle ABC, and therefore it is defined as an exterior angle. So what is the size of the exterior angle, angle E? According to this rule 8, the size of the exterior angle ACF is equals to E is equal to the sum of the two interangles that are not adjacent to it. This is the interangles gamma that is definitely adjacent to angle E. The two other interangles that are not adjacent to angle E are alpha and beta. So the size of angle E is equal to alpha plus beta, that is actually the sum of the two interangles that are not adjacent to it. Again, the size of angle E is alpha plus beta, that is the sum of the two interangles that are not adjacent to angle E. So E equals to alpha plus beta. So we can actually implement the new rule in our drawing. In our drawing, if we relate to the big associated triangle AQM, those three angles are defined as interangles, while this is angle AQP. Angle AQP is defined as an exterior angle in relation to the associated triangle AQM, why? Because it is located outside triangle AQM. So what is the size of the exterior angle AQM? According to angle AQP, what is the size of the exterior angle AQP? The size of the exterior angle AQP is equal to the sum of the two interangles that are not adjacent to it. This is angle AQM that is definitely adjacent to angle AQP. The two other interangles that are not adjacent to it are those two interangles. So according to rule 8, we get that the size of the exterior angle AQP is equal to beta plus beta. So already now, the size of the, so in relation to the big associated triangle AQM, angle AQP is defined as an exterior angle, and the size of angle AQP, the size of the exterior angle AQP is equal to the sum of the two interangles that are not adjacent to angle AQP. That is to say, it is equal to beta plus beta. Repeat again, according to rule 8, if we relate to the associated triangle AQM, angle AQP is defined as an external angle in relation to the associated triangle AQM. And according to rule 8, the size of the external angle AQP is equal to the sum of the two angles that are not adjacent to it. That is to say, is equal to beta plus beta. Beta plus beta is 2 beta. So the size of the external angle AQP is equal to 2 beta. According to rule 8, of course. But we have already found out that the size of the external angle AQP is 45 degrees. So we can substitute angle AQP by 45 degrees and get that 45 degrees equals to 2 beta. Here we will divide this equation by 2. And finally we get that the missing angle beta is equal to 45 degrees over 2 is 22.5 degrees. So we found out that the size of this missing angle beta is 22.5 degrees. The size of this angle beta is equal to 22.5 degrees. In the next step, we will focus on the right lower triangle QOM. So in the right lower triangle OQM, the sum of the angles must be equal to 180 degrees according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right lower triangle OQM? We have this angle that is a right angle, plus this is the angle beta that is equal to 22.5 degrees in its size, plus this missing angle OQM, in total the sum of those two angles must be equal to 180 degrees. And again, in the right lower triangle OQM, the sum of the three angles that is 90 degrees plus 22.5 degrees, plus the size of angle AQM, in total they must be equal to 180 degrees. Here we subtract 90 degrees from this equation and we get that 22.5 degrees equal 22.5 degrees plus the size of the missing angle OQM. In total they must be equal to 180 degrees minus 90 degrees is 90 degrees. So 22.5 degrees plus angle OQM, in total they must be equal to 90 degrees. Here we subtract 22.5 degrees from this equation, and finally we get that the size of the missing angle OQM is equal to 90 degrees over 90 degrees minus 22.5 degrees is equal to 67.5 degrees. So we found out that this is the missing angle OQM that is equal to 67.5 degrees in its size. We have the rule that says the vertex angles are equal to each other. And again, we have the rule that says that vertex angles are equal to each other. Those two angles alpha and beta are defined as vertex angles and they are equal to each other. That is to say, angle alpha equals to angle beta in its size. Likewise, we have the other pair of vertex angles. Those are the other two vertex angles. We define this angle as 1, we define this angle as 2. Those two angles are also defined as vertex angles and they are equal to each other and their sizes. So angle 1 equals to angle 2. Here we can implement this rule. In our drawing, we have those two vertex angles that are equal to each other in their sizes. That is to say, angle x equals to 67.5 degrees in its size. According to the rule that vertex angles are equal to each other, in our drawing we have angle x that is equal angle x and 67.5 degrees. There are two vertex angles and they are equal to each other in their sizes. That is to say, angle x equals to 67.5 degrees in its size. So the answer to the question is that the size of this angle p cubed is equal to x is equal to 67.5 degrees. So we finish with the first question. In the next step, I present to you the second question and we will solve the second question of this lecture. In the second question, our task is to find out the area of this vein shape. So, in the drawing, we have a quarter circle, a semicircle. This is a semicircle. PQ is the diameter of this semicircle, and it is equals to 10. And therefore the radius of this semicircle equals to 10 over 2, that is 5. In addition, we know that inside this semicircle we have the big square ABCD, and we have this small square MEFC. Again, our task is to find out the area of this vein shape. So first of all, we define the center of this semicircle. This point is point O. And we join points O and A together by straight lines. So point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of the semicircle, that is equals to 5 units in its length. And the radius of this semicircle equals to 5 units in its length. Likewise, we join points O and E together by straight line. OE is also the radius of this semicircle, that is equals to 5 units in its length. In the next step, we define the length of one side of square ABCD, SA. That is to say, AB equals to AD equals to DC equals to BC equals to A. We define the length of line segment OC as X. So what is the length of line segment OB? OB equals to BC minus OC. Again, what is the length of OB? OB equals to BC minus OC. So write it down. OB equals to BC minus OC. So OB equals to BC, BC equals to A, minus OC, OC equals to X. So in total, we should find out that OB equals to A minus X units in its length. ABCD is a square, we know that all the angles inside any square are right angles. So this is a right angle. Likewise, MEFC is also a square, and therefore this angle must be equal to 90 degrees in its sides. We will define the length of one side of this square, the small square MEFC is B. So MF equals to EF equals to FC equals to CM equals to B. EF equals to B, and CF also equals to B. In the next step, I'll copy the right angle ABO in the new page, and we implement on this right angle ABO the Pythagoras theorem. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, in the right angle ABO, the hypotenuse AO equals to 5 units in its length. side AB equals to A units in its length, and side BO equals to A minus X units in its length. So actually, this is the right triangle ABO that is coming from the original drawing. In this right triangle ABO, AO squared, that is the square, the hypotenuse, equals to AB squared plus BO squared. So write it down. This will be equation 1. According to equation 1, AO squared, that is the square, the hypotenuse, is equal to AB squared plus BO squared. AB is 5, therefore AB squared is 5 squared, that is 25. And it is equals to AB squared. AB is A, therefore AB squared is A squared. Plus BO squared. BO is A minus X, therefore BO squared is A minus X squared. So in total, according to equation 1, we actually found out that 25 equals to A squared plus A minus X squared. In the next step, I copy the right triangle OEF in a new page, and we will implement on it the Pythagoras theorem. Here by PT is implementation for Pythagoras theorem. The hypotenuse EO equals to 5 units in its length. That's also the radius of the semicircle. Side EF equals to B units in its length. What is the length of side O? What is the length of side OF of the triangle EOF? OF equals to X plus B. Certainly, this is the right triangle OEF, this is the copy from the original drawing. And this right triangle OEF, OE squared, that is the square of the hypotenuse, equals to EF squared plus FO squared. So I write it down. This will be equation 2. According to equation 2, OE squared, that is the square of the hypotenuse, is equal to OF squared plus EF squared. OE equals to 5, therefore OE squared is 5 squared, that is 25. And it is equals to OF squared. OF is X plus B, therefore OF squared is X plus B squared. Plus EF squared. EF equals to B, therefore EF squared is B squared. So in total, according to equation 2, we should find out that 25 equals to X plus B squared plus B squared. So in the next step, so we have, according to equation 2, 25 equals to X plus B squared plus B squared, while according to equation 1, 25 equals to A squared plus A minus X squared. In the next step, we create equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. So according to equation 3, according to equation 3, 25 according to equation 1 must be equal to 25 according to equation 2. According to equation 1 equals to a squared plus a minus a squared, and it is equal to 25 according to equation 2. 25 according to equation 2 equals to x plus b squared plus b squared. Here we will open the brackets on both sides of this equation, equation 3, and get that according to equation 3, a squared plus a minus x squared. A minus x squared equals to a squared plus x squared minus 2 times a times x, and it is equals to x plus b squared plus b squared. So x plus b squared equals to x squared plus b squared plus 2 times x times b plus b squared. So here we have x squared on both sides of this equation, so x squared will get cancelled. After we cancel x squared, in this side of equation 3 we have a squared plus a squared, that is 2a squared, minus 2ax, equals, in the other side of this equation 3 we have b squared plus b squared, that is 2b squared, plus 2bx. So here we divide this equation 3 by 2, and we get that according to equation 3, 2a squared over 2 is a squared, minus 2ax over 2 is minus ax, and it is equal to 2b squared over 2 is b squared, 2bx over 2 is bx. So total according to equation 3, if we found out that a squared minus ax equals to b squared plus bx. So here we relate ax to this equation, equation 3, and we get that according to equation 3, a squared equals to ax plus bx plus b squared. So here we subtract from this equation 3b squared, and we get that according to equation 3, a squared minus b squared equals to ax plus bx. We have the famous algebraic identity that says that a squared minus b squared equals to a plus b times a minus b. Here we have ax plus bx. So here we take x as a common factor from those two expressions. So inside the brackets we left only with a plus b. A is the length of one side of square ABCD, and b is the length of one side of the small square MECF. Therefore, now absolutely both of them are positive numbers, and when you add two positive numbers to each other, the result must be a positive number. That is to say, a plus b is a positive number, and therefore it is allowable to divide this equation 3 by a plus b. So we divide this equation 3 by a plus b. So in this side of this equation 3 we have a plus b times a minus b. So a plus b will get cancelled, and we left in this side of equation 3 only with a minus b. Here, on the side of the equation 3 we have x times a plus b, so a plus b will get cancelled, and we left only with x. Total, we found out that according to equation 3, a minus b equals to x. Here we will add b to this equation 3, and get that according to equation 3, a equals to x plus b. Here we subtract x from this equation 3, and get that according to equation 3, a minus x equals to b. According to equation 3, we found out that a minus x equals to b. So here we'll square both sides of this equation, equation 3, and we get that a minus x squared equals to b squared. The conclusion we found out that according to equation 3, a minus x squared equals to b squared. Our task is to find out the area of this green shape. So, what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape equals to the area of the big semicircle minus the area of the big square ABCD minus the area of the small square MEFC. Repeat again. The area of the green shape the area of the green shape equals to the area of the big semicircle minus the area of the big square minus the area of the small square. What is the area of the semicircle? Actually, the area of any semicircle equals to the area of the circle over 2. Therefore, the area of this semicircle must be equal to pi r square over 2. Pi r square over 2. But r, the radius of this semicircle, r is 5. Therefore, r square is 5 squared, that is 25. So total pi r square is 25 pi over 2. In conclusion, we found out that the big semicircle is equal to 25 pi over 2 square units. Minus the area of the big square ABCD. The length of one side of square ABCD is 8, therefore the area of the big square must be equal to a square minus the area of the small square. One side of the small square is equal to b units in its length, therefore the area of the small square must be equal to b square, so it is minus b square. So in total, we found out that the area of the green shape, that is the area that we are looking for in this question, it is equal to 25 pi over 2 minus a square minus b square. So it is 25 pi over 2. Here we take minus 1 out as a common factor from those two expressions. Inside the brackets, we left only with a square plus b square. So in total, we found out that the area of the green shape equals to 25 pi over 2 minus a square plus b square. According to equation 1, we only found out that according to equation 1, 25 equals to a square plus a minus x square. But we have only found out that a minus x square equals to b square. According to equation 3, a minus x square equals to b square. So we can actually substitute a minus x square in this equation 1 by b square from equation 3. And again, we can actually substitute a minus x square from equation 1 by b square from equation 3, because they are equal to each other. And we get that according to equation 1, 25 equals to a square, and a minus x square according to equation 3 is b square plus b square. So in total, according to equation 1, we actually found out that a square plus b square equals to 25. And therefore, we substitute a squared plus b squared in the expression of the green shape, in the expression of the area of the green shape. We substitute a squared plus b squared by 25. So 25 equals to a squared plus b squared according to equation 1. And we get that the area of the green shape in total equals to 25 pi over 2 minus a squared plus b squared. And a squared plus b squared equals to 25 according to equation 1. So in total, we actually found out that the area of the green shape, that is the area that we are looking for in this question, is equal to either 25 pi over 2 minus 25 square units, or in terms of numbers, the value of this expression is actually 14.27 square units in its size. Repeat again, we actually found out that the area of this green shape, it is equal to either 25 pi over 2 minus 25 square units. In terms of numbers, the area of this green shape equals to 14.27 square units in its size. So we finish with the second question. In the next step, I will summarize the lecture. We start with the first question, of course. In the first question, our task is to find out the size of this angle PQB is equals to x. We have to find out the value of x. So in the drawing, we have a quarter circle. AOB is a quarter circle. Therefore, this is an angle AOB that is equal to 90 degrees in its size. It is so in any quarter circle. In addition, we know that this is an angle APQ that is also a right angle. We also know that AP equals to PQ, and our test is to find out the size of angle PQB that equals to x. We have to find out the value of angle x. So in the first step, we completed the quarter circle to a semicircle. Again, we completed the quarter circle to a semicircle, and we defined this point as point M. And therefore, AM must be the diameter of the semicircle according to our construction. Repeat again. Because of the fact that we completed the quarter circle to a semicircle, AM must be the diameter of the semicircle. Okay, so AM is the diameter, it is absolutely a straight line. So if you focus on the right side of the straight line AM as point O, here the sum of the angles must be equal to 180 degrees according to all three. All three states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we extended line segment PQ by straight line. But the question is where the extended line segment PQ will touch the semicircle. Repeat again, the question is where the extended line segment PQ will touch the semicircle. We will assume that the extended line segment PQ will touch the semicircle at point L. Again, repeat again, according to our assumption, the extended line segment PQ touch the semicircle at this point L. Therefore, according to our assumption, we created peripheral angle APL that is equal to 90 degrees in size according to what is given as the question, and peripheral angle APL subtend on code AN. Again, peripheral angle APL subtend on code AN. But the problem is that AL cannot be the diameter of the semicircle because the center of this semicircle is at point O. And AL doesn't pass through point O, that is the center of the semicircle, and therefore it cannot be the diameter of the semicircle, because any diameter of the semicircle or circle must pass through the center of the circle or semicircle. And because of the fact that AF doesn't pass through the center of the semicircle, it cannot be the diameter of the semicircle. And it is a contradiction to Rule 5. Because according to Rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the semicircle. But peripheral angle APL subtend on AL that is not the diameter of the semicircle. So therefore it is impossible that the extended length segment PQ will touch the semicircle at point L, because we have contradiction to Rule 5. In the next step, we assume that the extended length segment PQ will touch the semicircle, will touch the circle at point H. Therefore, according to our assumption, we have here peripheral angle APH. We know that the size of a peripheral angle APH is 90 degrees, according to what is given as the question, and peripheral angle APH subtend on AH. But the problem is that AH is not the diameter of the semicircle, because AH doesn't pass through point O, that is the center of the semicircle. Therefore, it is impossible that the extended length segment PQ will touch the circle at point H, because we have contradiction to Rule 5. Because peripheral angle APL must be equal to 90 degrees must subtend on the diameter of the semicircle, because it is equal to 90 degrees in size, and peripheral angle APH subtend on AH that is not the diameter of the semicircle. So due to those contradictions to Rule 5, we have to conclude that the extended length segment PQ will touch the semicircle at point M and not to any other point. Again, the extended length segment PQ will touch the semicircle at point M and not in any other point. Now, we don't have any contradiction to Rule 5 anymore, because we have peripheral angle APM that is equal to 90 degrees in its size, and it subtend on AM, that is the diameter of the semicircle according to our construction. Okay, so the extended length segment PQ touches the semicircle at point M. In the next step, we join points A and Q together by a straight line. By joining points A and Q, get a right triangle that is also an associated triangle. Why? Because AP equals to PQ, and this angle is right angle. And we have the rule that in front of equal sides in the triangle there are equal angles. If we relate to the right and associated triangle, triangle APQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other. And you also know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and therefore it must be true in the right and associated triangle, triangle APQ. So which angles in the right and associated triangle, triangle APQ? We have this angle that is right angle, and alpha plus alpha is 2 alpha. So 90 degrees plus 2 alpha must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and found out that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. 2 alpha equals to 90 degrees. Here we divided this equation by 2, and found out that alpha equals to 90 degrees over 2 is 45 degrees. This is the missing angle alpha is equals to 45 degrees in size, and this is also angle alpha is equals to 45 degrees in size. In the next step, we prove that those two right angles can go into each other according to side angle side rule. So I'm going to prove that the right upper triangle AOQ can go into the right lower triangle, triangle OQM, according to side angle side rule. So why those two right angles can go into each other? First of all, AO equals to OM, they are both the area of the semicircle, and therefore they are equal to each other. In addition, those two angles are both right angles, and therefore they are equal to each other. And finally, OQ is a common side that belongs to both triangles. So we can find out that OQ equals to itself is a common side that belongs to both triangles. So if you prove that those two right angles can go into each other according to side angle side rule. That is to say, if you prove that those two sides and the angle that is included between those two sides in the right upper triangle AOQ correspond equal to those two sides and the angle that is included between those two sides in the right lower triangle, triangle OQM. And therefore those two right angles can go into each other according to side angle side rule. Okay, again, as we found out that we prove that the right upper triangle AOQ can go in, this is the same congruent to the right lower triangle, triangle OQM according to side angle side rule. And from the fact that those two right angles can go into each other, we will derive that AQ equals to QM. Actually, AQ equals to QM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other. And therefore those two corresponding sides AQ and QM must be also equal to each other in their lengths. And again, we prove that, actually conclude that AQ equals to QM. So if you relate to the big associated triangle AQM, triangle AQM is an associated triangle because AQ equals to QM. So in the big associated triangle AQM, in front of those two equal sides, you have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. So those two angles are both equal to beta. And here I presented to you a new rule and implemented the new rule in our drawing. The new rule is rule 8. According to rule 8, an external angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. So in the drawing we have triangle ABC that could be in a triangle. Those angles alpha, beta and gamma are defined as interangles because they are located inside triangle ABC. While this is angle ACF, this equals to E according to our definition, is located outside triangle ABC and therefore it is defined as an external angle. So what is the size of the external angle? Angle E. According to this rule 8, the size of the external angle E is equal to the sum of the two interangles that are not adjacent to it. This is the internal angle gamma that is definitely adjacent to angle E. The two other interangles that are not adjacent to angle E are those two angles, alpha and beta. And therefore, according to rule 8, the size of external angle E equals to the sum of the two interangles that are not adjacent to it. That is to say, it is equal to alpha plus beta. And at the end, the size of angle E equals to alpha plus beta according to this rule, rule 8. So we implemented rule 8 in our drawing. In our drawing, if we relate to the big associated triangle AQM, those three angles are defined as interangles because they are located inside triangle AQM, while this is angle AQP that is defined as an external angle of triangle AQM because it is located outside triangle AQM. So what is the size of the external angle AQP? According to rule 8, the size of the external angle AQP must be equal to the sum of the two interangles that are not adjacent to it. This is angle AQM that is definitely adjacent to angle AQP. The two other angles that are not adjacent to angle AQP are those two angles. Therefore, the size of the external angle AQP according to rule 8 must be equal to beta plus beta. And again, according to rule 8, if you relate to the big associated triangle AQM, the size of the external angle AQP must be equal to beta plus beta, that is 2 beta. But we already found out that the size of the external angle AQP is equal to 45 degrees. Therefore, we can substitute angle AQP by 45 degrees. Substitute angle AQP by 45 degrees. And finally found out that 45 degrees equals to 2 beta. Here we divided this equation by 2 and finally found out that beta equals to 45 degrees over 2 is 22.5 degrees. So this is the missing angle beta that is equals to 22.5 degrees, and this is angle beta that is also equals to 22.5 degrees in its size. In the next step, we focus on the right lower triangle OQM. In the right lower triangle OQM, the sum of the angles must be equal to 180 degrees. It is true in any triangle, and therefore it is true in triangle OQM. So which angles we have in the right lower triangle OQM? We have this angle that is 90 degrees, plus this angle beta that is equals to 22.5 degrees, plus this missing angle OQM. In total, the sum of those angles must be equal to 180 degrees. So again, in the right lower triangle OQM, 90 degrees plus 22.5 degrees plus the size of the missing angle OQM, in total must be equal to 180 degrees. Here we subtract the 90 degrees from this equation, and finally found out that 180 degrees minus 90 degrees is 90 degrees, so 90 degrees equals to 22.5 degrees plus the size of the missing angle OQM. Here we subtract 22.5 degrees from this equation, and finally found out that the size of the missing angle OQM equals to 90 degrees minus 22.5 degrees is 67.5 degrees. So if we found out that the size of this missing angle OQM is equal to 67.5 degrees. In the next step, I presented to you the rule that says that vertex angles are equal to each other. Those two angles, alpha and beta, are defined as vertex angles, and therefore they are equal to each other. Alpha equals to beta. Likewise, those two angles are also defined as vertex angles, and they are equal to each other. That is to say, angle 1 equals to angle 2 in its size. So we can implement the rule in our drawing. In our drawing, those two angles are also defined as vertex angles, and therefore they are equal to each other. That is to say, x equals to 67.5 degrees in its size. Only to the rule that vertex angles are equal to each other, x equals to 67.5 degrees in its size. So the answer to this question is the size of the missing angle PQB is equal to x is equal to 67.5 degrees. So we finish with the first question. In the next step, I presented to the second question and solve the second question of this lecture. In the second question, our task is to find out the area of this grain shape. In the drawing, we have a semicircle. PQ is the diameter of the semicircle, that is equals to 10, and therefore the radius equals to 5. Inside this big semicircle, we have the big square ABCD and the small square MCFE. Again, our task is to find out the area of this grain shape. We define the center of this semicircle. This point is point O. We join points O and end together by side line. Point O is the center of the semicircle. Point A is the point on the semicircle itself. Therefore, OA is the radius of the semicircle. This is equal to 5. The radius of the semicircle equals to 5. Likewise, we join points O and D together by side line. OE is also the radius of the semicircle. This is equal to 5. In the next step, we define the length of one side for square ABCD. SA. That is to say, AB equals to BC equals to CD equals to DA equals to A. And we define one side of the small square MEFC as B. That is to say, ME equals to EF equals to FC equals to CM equals to B. So MEFC is a square, and therefore this angle is right angle. ABCD is a square, and therefore this angle is right angle. So we define the length of the short line segment OCSX, and therefore BO must be equal to BC minus OC. Again, BO equals to BC minus OC. So BO equals to BC, that is A, minus OC, that is X. So in total, BO equals to A minus X units in its length. Likewise, OF equals to X plus B. So in the next step, I copied the right triangle AOB in a new page, and we implemented the Pythagoras theorem on this right triangle AOB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the slopes of the perpendiculars. So this is the right triangle AOB that according to the original drawing. According to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BC, to AB squared plus BO squared. AO is 5, therefore AO squared is 5 squared, that is 25, and it is equals to AB squared. AB is A, therefore AB squared is A squared, plus BO squared. BO is A minus X, therefore BO squared is A minus X squared. So according to equation 1, in total we found out that 25 equals to A squared plus A minus X squared. In the next step, I copied the right triangle OEF in a new page, and we implemented the Pythagoras theorem on this right triangle OEF. Okay, this is the right triangle OEF that according to the original drawing. The hypotenuse O equals to 5 units in itself. It is actually also the radius of the semicircle. EF equals to B, and F equals to X plus B. According to the Pythagoras theorem, in this right triangle OEF, OE squared, that is the square of the hypotenuse, equals to EF squared plus OF squared. OE is 5, therefore OE squared is 5 squared, that is 25, and it is equals to OF squared. OF is X plus B, therefore OF squared is X plus B squared, plus EF squared. EF is B, therefore EF squared is B squared. So in total, according to equation 2, we should find out that 25 equals to X plus B squared plus B squared. This is according to equation 2, while according to equation 1, we have only found out that 25 equals to A squared plus A minus X squared. In the next step, we created equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. So again, we created equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. 25 according to equation 1 equals to a squared plus a minus x squared. It must be equal to 25 according to equation 2. 25 according to equation 2 equals to x plus b squared plus b squared. Here we open the brackets on this side on both sides of this equation 3. We found out that according to equation 3, a squared plus a minus x squared. A minus x squared equals to a squared plus x squared minus 2a times x. And it is equal to x plus b squared. X plus b squared equals to x squared plus b squared plus 2 times x times b plus b squared. Here we have x squared on both sides of this equation, so x squared we can cancel. After we cancel x squared, on this side of equation 3 we left only with a squared plus a squared, this is 2a squared minus 2ax. While on the other side of this equation 3 we left with b squared plus b squared, that is 2b squared plus 2bx. Here we divided this equation 3 by 2 and found out that 2a squared over 2 is a squared minus 2ax over 2 is ax, and it equals to 2b squared over 2 is b squared and 2bx over 2 is bx. So in total, according to equation 3, we found out that a squared minus ax equals to b squared plus bx. Here we added ax to this equation 3, and found out that a squared equals to ax plus bx plus b squared. Here we subtracted b squared from this equation 3, and finally found out that a squared minus b squared equals to ax plus bx. We have the famous trigonometric identity that says that a squared minus b squared equals to a plus b times a minus b. Here we have ax plus bx. Here we took out x as a common factor from those two expressions, so inside the brackets we left only with a plus b. We know that a is the length of the one side of the big square of square BCD, and b is the length of one side of the small square, square MEFC. So the length is a positive number. If we add two lengths together, the result must be also a positive number. So a plus b is a positive number. Therefore, it is allowable to divide this equation 3 by a plus b, because it can never be equal to 0, it must be a positive number. So we divided this equation 3 by a plus b. So here a plus b will get cancelled, and we left only with a minus b. Here also a plus b will get cancelled, and we left only with x. So according to equation 3, we actually found out that a minus b equals to x. Okay, here we added b to this equation, and we found out that a equals to x plus b. Here we subtract the x from this equation, and finally found out that a minus x equals to b. Here we squared both sides of this equation 3, and finally found out that a minus x squared equals to b squared. Okay, again, according to equation 3, we actually found out that a minus x squared equals to b squared. Our test is to find out the area of this green shape. So what is the area of the green shape? From the domain, it is very easy to see that the area of the green shape in total equals to the area of the big semicircle minus the area of the big square minus the area of the small square. Meaning again, the area of this green shape in total is equals to the area of the big semicircle minus the area of the big square minus the area of the small square. The area of the semicircle is pi r square over 2. R is 5, therefore pi r square over 2 is 25 pi over 2. The area of the big square is a square, because one side equals to a, so it is minus a square. One side of this small square is b, therefore the area of this small square is b square, so it is minus b square. So in total, we found out that the area of the green shape equals to 25 pi over 2 minus a square minus b square. So it is 25 pi over 2. Here we took minus 1 as a common factor from those two expressions, so inside the brackets we left only with a square plus b square. We have only found out that according to equation 1, 25 equals to a square plus a minus x square. And we also found out that according to equation 3, a minus x square equals to b square. So here, according to equation 3, a minus x square equals to b square. So here, so we can substitute a minus x square by b square. We can substitute a minus x square in this equation 1 by b square from equation 3, because a minus x square equals to b square. We did it, and we found out that according to equation 1, 25 equals to a square, and a minus x square is b square. So in total, according to equation 1, 25 equals to a square plus b square. So therefore, we can substitute a square plus b square by 25, because 25 equals to a square plus b square according to equation 1. We did it, and we found out that 25, the area of the green shape equals to 25 pi over 2, and minus a square plus b square is minus 25. So in total, we found out that the area that we're looking for in this question, that is the area of this green shape, is equal to either 25 pi over 2 minus 25 square units in size. In terms of numbers, the value of this expression is 14.27 square units in size. Repeat again, we actually found out that the area of this green shape, that is the area that we're looking for in this question, is equal to either 25 pi over 2 minus 25 square units in size. So in terms of numbers, the area of this green shape is equal to 14.27 square units in size. Okay, thank you very much.